Hello, yeah. When you analyze your data, you often ask yourself, which statistical test should I choose, right? So in this video, I want to show you how to choose a statistical test using R by asking three questions. Okay. Question one, what type of outcomes? Is it continuous? Is it score, blood pressure, weight? Or is it categorical? Yes or no, success, failure, disease or no disease? Question two, how many groups or time points? One, two, or three, or more? Question three, are observations independent or paired? One, independent, different participants in each group. Paired, the same participant measured repeatedly or matched pairs. So here I'm going to show you a script demonstrate common choices for simple study designs. Okay. All right. So let's first load in the package ggplot2 because we do want to do some visualization. Okay, so let's create an example data set a random seed, create an ID from 1 to 60, group as factor, and the control treatment A, treatment B, each have 20, and then we generate normally distributed outcomes, and we have scores, pre-scores, and then the post-score is the pre-score at another random errors, normally distributed, and we calculate the differences between the post-score minus the pre-score. And this is what the data set look like, ID, group, outcome, pre-score, post-score, difference. Okay. And you can just calculate a quick calculation about the descriptive statistics on each variable. And so always inspect the data before testing. So let's plot out the data, outcome against group, and then this is what it looked like. You got three groups. You got a continuous outcome, look like that. Okay, so you get continuous outcome, and then case one is two independent groups. So let's just say group control versus treatment A. We can create another group, another data set of two groups from the original data, and then we just say group include control and treatment A. Okay, and then now there's two groups, whether it's a parametric or non-parametric. So we can use the Welch two-sample t-test for the equivariance, non-equal variances. So let's see, do the t-test because it's continuous, and the outcome against group. Data equal to two groups, then we see that the output from the Welch two-sample t-test. Okay, and rank-based test, if it's not normally distributed, then we can use a Wilcoxon test, and you can see the output over there. And keep in mind the Wilcox test compare medians instead of the means as the t-test. Okay, and case two is two paired measurements. Pre-score versus post-score, and we can do that, just use the t-test data post-score and data pre-score, and we say paired equal to true. This gives you the paired t-test. And also you can use the rank-based option using the Wilcoxon signed rank test. Use Wilcoxon dot test pre-score, post-score, and pre-score, and the paired equal to true. Okay, and then you have equivalent approach, analyze the within person differences. So you can just be able to calculate the differences and put in the data set. It's called the diff. Okay, so we just run the t-test, and the null hypothesis mu equal to 0. Okay, and you similarly can do Wilcox test on that. Okay, give you the same result. Okay, and for paired tests, we want to inspect the differences. So we can do a histogram, do the data of the diff, and then give some title and X labels. You can see post-score minus pre-score. It looks like okay, looks like a normal distribution, a little bit skewness, but that's okay. You want to do more QQ plot, QQ norm plot. So you can see it's mostly a lot in the straight line with a little bit off in the tail. Okay, and you can add a QQ line. So it's okay. Yeah. All right. Case three or more independent groups. We're comparing control treatment A, treatment B. What you can do is if you use parametric option, so the data follow normal distribution, we can use the ANOVA model. So ANOVA fit is from AOV, outcome against the group, data equal to data, and you can print out the summary of the outputs. You can do some post-hoc comparisons after ANOVA. For example, 2-key HSD of ANOVA, it will give you the adjusted p-value there and tell you which two groups are different. Okay. And if the variances are clearly unequal, then you can use the Welch ANOVA using the function for the one-way dot test. The syntax is the same. Okay. You can use a rank-based option. It's the Kruskal-Wallis test. Kruskal.test, outcome, regress non-group, and data equal to data. Okay. You can do pairwise follow-up test after the Kruskal-Wallis test. Use a pairwise dot Wilcox dot test, and x equal to data at outcome, g equal to data at group, and then p at adjust method equal to home. That's another multiple testing adjustment. Okay, and give you the adjusted p-values. Okay, and case number 4 is 3 or more pair measurements, and then this is the sample, the same subject measured at pre, mid, and post. We have to create a repeated data set. So subject would repeat 1 to 20, each equal to 3. The time fact pre, mid, and post. Time equal to 20, level equal to pre, mid, post, and generate scores. And this is the head of the data set created. You can see the subject ID 111222, so repeat multiple times. This is the long format of a longitudinal data set. Okay. So if say the data follow normal distribution, you can use a repeat measure ANOVA. The syntax AOV score tier dot time plus error of subject / time, and data equal to repeated data, and this is the summary. And then you can do rank-based option, which is called the Friedman test, which is the non-parametric repeated measure ANOVA. So Friedman dot test score regress on time given a subject and data equal to repeated data. Okay. And now if you have categorical outcome, so we create a categorical data from the data frame, 3 groups, group and treatment, and then you get equal to 50, response equal to no 20, response yes 30, response no 5, response yes to 45. And this is table data, and this is what it looked like. So you get a 2x2 table there. And you can do a proportion plot, ggplot. It looked like that. Seems to be a little bit different proportion. And then you can do a chi-square test because it's categorical. Okay, and you get chi-square test result. And you can inspect the expected values by chi result at expected. So the rule of thumb is you want all the expected cell count greater than 5, or at least 80% of those cells with expected cell counts. If they don't meet that criteria, then the chi-square test is not reliable. So you have to go for the Fisher's exact test when expected counts are small. So this is, if any less than that, then you can use Fisher's test. Okay. Okay. So this is a assumption checking, a short practical guide. Do not use the test from a Shapiro-Wilk p-value alone. Inspect the design, sample size, plots, outliers, and variances. Okay, so visualization is important here. For paired data, inspect the distribution of the difference. And useful plots include histogram, QQ norm, QQ line, box plot. And the observation must be independent at the property level. If you have covariates, clustering, missing repeated measurements, or factorial design, consider regression or mixed effects models. For example, you get LM post-score regress sum group plus pre-score data equal to data. Okay, so this is a quick decision table. Here you get outcomes continuous, categorical, or design is independent or paired, two independent, two paired, 3 plus, independent 3 plus, paired measurement, independent groups, and you get parametric test, t-test, or non-parametric test, Wilcoxon test, etc., etc. And use Fisher's exact test when the contingency table is sparse or expect cell counts are small. And remember, 1, identify the outcome type. 2, count the groups or time points. 3, determine whether observations are independent or paired. 4, inspect assumptions and choose a suitable analysis. The independent versus paired distinction is fundamental to selecting the appropriate test. So basically look at the type of data, study design, and number of groups, and check the assumptions. Okay, I hope this is helpful, and you know which statistic to choose from your next data analysis project. Thanks for watching.